So we start part 2 of double angle, half angle, and power reducing formulas with the latter power reducing formulas. Power reducing formulas are used to take a trig function raised to an exponent and rewrite it using an expression without an exponent. And when you take a Calculus 2 class, you will find value for this when you are evaluating integrals. But notice our first formula, sine squared of theta is rewritten as 1 minus the cosine of 2 theta over 2. Again, notice an exponent of a square here, but no exponent higher than 1 over here. And of course, that's true for all three of these. So you'll be given problems that have a sine or a cosine or a tangent raised to a power, but you need to rewrite with trig expressions not raised to a power. But what we want to do on this page is prove these three formulas. So where I'm going to start is I'm going to write the formula for cosine of 2 theta. That's actually what's been used to prove all three of these is a different version of cosine of 2 theta. So if you recall, cosine of 2 theta, just going on memory, is equal to cosine squared of theta minus sine squared of theta. That's one of the versions. Another version is if we replace the cosine squared of theta with 1 minus the sine squared of theta, Pythagorean identity, that'll give me 1 minus 2 sine squared of theta. Or, instead, going back to the top, we can replace sine squared of theta with 1 minus the cosine squared of theta, and I distribute that negative inside. That's going to give me 2 cosine squared of theta minus 1. So what I want to do is start with just one of these. How about we start with this one, the 1 minus 2 sine squared of theta. Okay, and I'm going to write what I have. Cosine of 2 theta, parentheses not required, equals 1 minus 2 sine squared of theta. Now what I want to do is solve for the sine squared of theta. So the first thing I'm going to do is subtract 1 from both sides of this expression. So I have cosine of 2 theta minus 1 is equal to negative 2 sine squared of theta. Now remember the goal is to solve for sine squared of theta. So the next thing I'm going to do is divide both sides by negative 2. That gives me cosine of 2 theta minus 1 divided by negative 2 is sine squared of theta. So we did it. We solved for sine squared of theta, but this one does have an extra issue. You don't like to leave negatives in the denominator. So how do I solve that? I take it to the numerator, which is going to make it distribute inside. It's going to turn this cosine of 2 theta into negative, and this negative 1 positive. So it would be okay if I reverse the order and say 1 minus cosine of 2 theta over 2. Again, what I did, I took that negative to the numerator. That made that a negative cosine of 2 theta and a positive 1. And I just reversed the order using the commutative property of addition. And if you'll notice, that is your first property listed. Okay, now in green, let's try this again. Okay, I'm going to take this formula, this representation of cosine of 2 theta, and say cosine, how about cosine first? Cosine of 2 theta is equal to 2 cosine squared of theta minus 1. And I'm going to do the same thing. I'm going to solve for cosine squared of theta. So to do that, I'm going to add 1 to both sides. I get cosine of 2 theta plus 1 is equal to 2 cosine squared of theta. Now I've got to get rid of the 2. So I have cosine of 2 theta plus 1 divided by 2 is cosine squared of theta. Okay, so I'm just manipulating the formula. That's all I'm doing. So really, the power reducing formulas are just the double angle formulas written in a different format. Okay, so if you'll notice that is your second one. The question is, how do we get the third one? How do we get tangent squared? How about let's change to purple and talk about it. All right, so tangent squared of theta, I'm sure everybody agrees I could rewrite that as sine squared of theta divided by cosine squared of theta. Right? We know that's true. all right, because of the quotient identity. Now, sine squared, we've already proven, is 1 minus the cosine of 2 theta over 2, or you can look right up here. So that's 1 minus the cosine of 2 theta divided by 2 over, now let's write cosine squared. I got that right up here in green, or right up in the middle here. That's 1 plus the cosine of 2 theta divided by 2. My next step would be to invert our fraction that we're dividing by and multiply. That would give me an equivalent statement of 1 minus the cosine of 2 theta over 2. Flip this guy, 2 over 1 plus the cosine of 2 theta. And that's equivalent to the 2's cancel. That'd be 1 minus the cosine of 2 theta over 1 plus the cosine of 2 theta. And that is the end of that. And we did this one just like verifying an identity. The other two, the red and the green, the sine squared of theta and the cosine squared of theta, we just manipulated a formula. All we did was rearrange it. But now tangent squared of theta, we actually verified the identity by starting with the left-hand side and making it equal the right-hand side. So the problems that want you to use power-reducing formulas read like this. They want you to write an equivalent expression for cosine squared of x that does not contain trigonometric functions greater than 1. So what we need to do is look up the formula for cosine squared of x. If I go back to the previous page where I proved everything, here it is right here. I'm going to highlight it right here. Cosine squared of theta is 1 plus cosine of 2 theta over 2. Okay, so if I do cosine squared of x, that's going to be 1 plus the cosine of 2x over 2. And then, did we do it? Did we write cosine squared of x as a trigonometric function or expression that does not have an exponent greater than 1? Well, sure, this exponent is just 1. We're done. That's all that's required there. Now, you know the problems are not going to be that simple. But that's it. That's all that's required for that problem. So let's take a look at a problem more like which would be in the homework. Write an equivalent expression for cosine to the fourth of x that does not contain trigonometric functions greater than 1. Well, we don't have a formula for cosine to the fourth of x. Can we handle it? You bet. We can write it as cosine to the fourth of x is equal to cosine squared of x times cosine squared of x. Right? That is cosine to the fourth of x. And now I could use the formula twice. Okay, so this is going to be 1 plus the cosine of 2x over 2 times 1 plus the cosine of 2x over 2. You want to make sure you got that formula right? Let's go back a page or two. There it is. Again, 1 plus the cosine of 2x over 2. The sine squared is 1 minus the cosine of 2 theta or 2x over 2. So now, didn't we just write cosine to the fourth of x as an expression without a power greater than 1? Well, no, not really, because this is multiplication. I do have a cosine squared in here, because if I simplify this, this is equivalent to 1, so that times that, plus the cosine of 2x, plus another cosine of 2x, when I multiply that one times that one, plus, and then cosine of 2x times cosine of 2x is cosine squared. Be super careful here of 2x. That's not going to be like 4x squared. This is not multiplication of angles. You're just doing cosine times cosine, and that gives you cosine squared of your common angle. Okay, if they didn't have the same angle inside, we couldn't even multiply them together. We just have to sit them next to each other. We couldn't write it as squared, is what I'm trying to say. And don't forget to multiply the denominator. 2 times 2 is 4. If I simplify that, it's going to give me 1 plus the cosine, well, actually 1 plus 2 cosine. There we go. So that's going to give me 1 plus 2 cosine of 2x plus cosine squared of 2x over 4. Now we're not done with this problem, right? Because I got an issue right here. I'm not allowed to keep a square in my answer, so I have to keep going. I'm going to use my cosine formula again. This is 1 plus 2 cosine of 2x plus, okay? Remember, that formula is a fraction. I've got the formula written right here if you want to take a look at it. And it says 1 plus the cosine of 2x over 2. But keep in mind, that formula is if there was an x inside. We have a 2x inside of ours, so I'm going to have to double that and say 4x over 2. So remember the formula says, in blue, that cosine squared, let's just say x, is 1 plus the cosine of double the angle over 2. So if I have a 2x inside of here, that's going to be 1 plus the cosine of double 2x, which is going to give me 4x, is what I've got down here, over 2. And don't forget, remember, all that's still over 4. Now here we got a complex fraction. I have a fraction inside another fraction. So I'm going to have to combine these numerators together and get a common denominator, okay? So I'm going to multiply 1 by 2 over 2. I'm going to multiply 2 cosine of 2x by 2 over 2. And then this guy is already over 2, okay? So I'm going to keep going across to the right, see if I can fit it all in here. It's going to give me 2 plus 4 cosine of 2x plus 1 plus the cosine of 4x all over 2, and that's all over 4. Well, what a mess. Okay, so I've got 2 plus 4 cosine of 2x plus 1 plus cosine of 4x all over that common 2. Okay, now I'm going to add like terms. And what I need to do is I need to get rid of what we have up here. I'm going to get rid of these 2 lines, or 3 lines, so you can follow what I'm doing, okay? So just a second. Take a look at what you have on paper and make sure that makes sense. All right, here we go. We're going to continue. So I'm going to add like terms. I've got this 2, then I can add to this 1 over here. It's going to give me 3 plus, I got a 4 cosine of 2x. It's a 2. Plus, I know it's so hard to see, cosine of 4x. That's over 2. And that's being divided by 4. Remember that 4 is over 1, so that's times 1/4. So my final answer, y'all, is 3 plus 4 cosine of 2x plus the cosine of 4x, all divided by 8. Have we done what we're supposed to do? Did we rewrite cosine to the 4th of x as a trigonometric function without exponents greater than 1? Okay, and I read this, it's write an equivalent expression for cosine of the 4th of x that does not contain trigonometric functions of exponents greater than 1. Okay, I think I left out the word exponents. But there we go, 3 plus 4 cosine of 2x plus cosine of 4x all over 8. Those are fun problems. And last on the list for formulas in this lecture, in this section, are the half angle formulas. So notice you're talking about half of an angle inside, that's why I call them half angle. Sine of alpha over 2 is equal to plus or minus the square root of 1 minus cosine of alpha over 2. Now when you use these formulas, I'm going to go ahead and say this, your final answer doesn't contain a plus or a minus. You have to correctly decide which one of those is correct. Is it the positive or is it the negative? And that's if you know, okay? That's if you know where the angle is located. So the sine of whatever angle you're dealing with. It gives us a hint to prove this. We won't prove all of them, but let's maybe talk about sine of alpha over 2. Where does that proof come from? It says begin with the power reducing formula. Okay, so let's begin with the power reducing formula for sine squared. So I remember that sine squared of theta is equal to 1 minus the cosine of 2 theta over 2. Remember, we just used that, okay? Now, it says replace the angle theta with alpha over 2. So I would say sine squared of alpha over 2 is 1 minus the cosine of 2 times alpha over 2 divided by 2. Now if you'll notice, this 2 and this 2 cancel each other out. So now I have sine squared of alpha over 2 is 1 minus the cosine of alpha, parentheses not required, over 2. And now if I take the square root of both sides to get rid of the square, I have sine of alpha over 2 is equal to plus or minus, because I'm taking the square root of both sides, 1 minus the cosine of alpha over 2. And that gives us our first formula right up here. And the proofs for all these are very similar. Okay, so they just come from the power reducing formulas, and the power reducing formulas just come from the double angle formulas. And remember, the double angle formulas just come from the sum difference formulas that we had in a previous section. So the next problem, I would actually like to use one of these formulas. So we're supposed to use the half angle formula to find the exact value of the expression. So sine of 105 degrees. Now if you'll recall, 105 degrees is not anywhere, well, it's on our unit circle, but it's certainly not one of the values we have memorized. What we have memorized is 90 degrees, and then 30 degrees later 120 degrees. So 105 degrees is not one of the regular values on the unit circle. But it's asking us to use the half angle formula to do this. So the question is, what is 105 degrees half of? That's really the question. So how about 210 degrees? Now you have to think about this. Is 210 one of the regular values on your unit circle? Okay. What do you think? Well, 210 degrees is 30 more than 180, and we have everything, 30, 60, 90, all that's well covered. So yes, 210 degrees is on our unit circle. So how do we handle this? We could say this is sine of 210 degrees over 2. That is 105 degrees, right? And then we just plug into our formula. Now remember, the formula for sine, you want to go back and look at it right there, highlighted in green, is plus or minus the square root of 1 minus the cosine of whatever our alpha is over 2. Okay, so again, you want to write it over here. So the sine of alpha over 2 is plus or minus the square root of 1 minus the cosine of alpha over 2. So for our formula, that's going to be plus or minus the square root of 1 minus the cosine of 210 degrees over 2. So I continue on. That's plus or minus the square root of 1 minus. Now we need to know the cosine of 210 degrees. Where 210 degrees is right here. It's equivalent to 7 pi over 6. Again, that's 180 degrees plus 30 more. The cosine value is the x value right there. The x value right there is negative square root of 3 over 2. And that's all divided by 2. I continue to simplify. You got plus or minus the square root. Okay, this turns into plus, and I need to write a common denominator up here, so I'm going to multiply the 1 by 2 over 2. So now I have 2 plus the square root of 3 over the common denominator 2, also divided by 2. Move across, that's plus or minus the square root of 2 plus the square root of 3 over 2 times this guy. I'm going to flip upside down. 1/2 gives me plus or minus the square root. That's going to be 2 plus the square root of 3 over 4. You can take the square root of 4, so plus or minus the square root of 2 plus the square root of 3 all over 2. Now remember, we can't have a plus or minus answer. It's one or the other. So my final answer, let's write this thing in blue. Now, where is 105 degrees. Remember, the answer we're finding is the sine of 105 degrees. 105 degrees is in quadrant 2, right? Is sine positive or negative in quadrant 2? Well, it's positive because it's a y value. So our answer is positive, the square root of 2 plus the square root of 3 all over 2. That is our final result. You can certainly check that by plugging that value in your calculator and also evaluating the sine of 105 degrees and see if you don't get the same decimal. In this problem, we're supposed to write the expression as the sine, cosine, or tangent of a double angle and then find the exact value. So if you look at this problem, we can't go straight to the unit circle and evaluate this because pi over 12 is not one of our memorized values on the unit circle. So they're asking us to write this as a double angle. What we have now is a trig function to a power. So we could use our power reducing formula. If you'll recall, that sine squared of theta is 1 minus the cosine of 2 theta over 2. If you need to go back and take a look, let me show you. Those are half angle. There's the power reducing. So sine squared is 1 minus the cosine of 2 theta over 2. So I'm looking at this first one right here. I'm trying to move around. How about that guy right there? Okay. So let's go back. There it is, 1 minus cosine of 2 theta over 2. So I'm going to replace this expression here with 1 minus the cosine of 2 times pi over 12 over 2. So my entire expression is 1 minus 2, and then again I'm replacing sine squared of pi over 12 with 1 minus the cosine of 2 times pi over 12 over 2. Alright, and I continue to simplify. That's 1 minus 2. Alright, so this 2 and this 12 cancel to get pi over 6. Gives me 1 minus the cosine of pi over 6 over 2. I continue simplifying. That's 1 minus 2. 1 minus, now the cosine of pi over 6. Remember, cosine is the x value, so square root of 3 over 2. All divided by 2. Continuing on, I have 1 minus 2. Now, we need a common denominator to combine these two values in the numerator together, so that's going to give me 2 minus the square root of 3 over 2, and that is all divided by 2. We could put that over 1 because we know we're going to have to invert and multiply. So that continues to give me 1 minus 2, parentheses 2 minus the square root of 3 over 2 times 1 over 2 when I flip, which gives me 1 minus 2 times 2 minus the square root of 3 over 4. This 2 and this 4 cancel, give me a 2. And I also need a common denominator of 2, so I'm going to multiply this by 2 over 2. So now I have 2 minus, and then we have 2, and distribute this minus plus the square root of 3 over 2, which is just going to give me a final answer of the square root of 3 over 2. Now we could check this with our calculator to make sure it's correct. We could do 1 minus 2 and then do sine squared, make sure you're in radian mode, of pi over 12 and see that you don't get the same answer is equivalent to square root of 3 over 2. Since we're to use the figures to find the exact value of the trigonometric function, notice there's only one function given, the sine of alpha over 2. So that means we're going to need to use the figure that's got alpha in it. So this figure with theta, we don't need that for this particular problem. Probably the next problem we'll use it. But alpha is the guy that we need right here. So the next step would be to write the formula for sine of alpha over 2. Again, notice that's a half angle formula. I will give you these on the test, but it's plus or minus the square root of 1 minus the cosine of alpha over 2. So this is equivalent to plus or minus the square root of 1 minus the cosine of alpha over 2. Okay, Now this triangle we've got drawn over here, this one is for alpha, not for alpha over 2. That's why we must use the formula. So I continue by plugging in. I have plus or minus the square root of, this is going to be 1 minus, now the cosine of alpha. Remember, cosine is adjacent over hypotenuse. Well, unfortunately, we don't have the hypotenuse, but we can certainly find it by using the Pythagorean identity. So I have 7 squared plus 24 squared is equal to the hypotenuse, or c squared. It gives me 49 plus 576 is equal to c squared. Add 49 and 576, I get 625 is equal to c squared. So c, now if I just solve in an equation, it would be plus or minus 25. But since we're talking about the length of the side of a triangle, it's just the positive. So I know that this length is 25. And now I substitute. So cosine of alpha, again, if you'll recall, is adjacent, which is 24, over hypotenuse, which is 25. And that's all divided by 2. Now to combine this complex fraction together, the next thing I need to do is find a common denominator, which is 25. So I have 25 over 25, and that gives me plus or minus the square root of 25 minus 24 is 1 over 25 divided by 2. I continue across, that's plus or minus the square root of 1 over 25 times, I'm going to invert my 2, so I'm multiplying by 2. That's plus or minus the square root of 1 over 50. Okay, now the square root of 50 I can reduce. So this is plus or minus the square root of 1 over, now 50 I can write as 25 times 2. And I can take the square root of 1 over 25. So this gives me plus or minus 1/5. The square root of 2 remains underneath. And then I can rationalize by multiplying by the square root of 2 over the square root of 2. So my final answer is looking like plus or minus the square root of 2 over, and then this is going to be 5 times 2 when I multiply those together, which is 10. So the answer to this sine of alpha over 2 is plus or minus the square root of 2 over 10. Now, the fact is it can't be both positive and negative. So before we jump in there too quickly, let's decide which one of these we're dealing with. Okay, and you're talking about sine of alpha over 2. Now sine, when you're talking about a triangle, all the lengths of these sides are positive, therefore the ratios are positive, so this angle is positive, or this ratio is positive. So you're talking about the square root of 2 over 10, the positive only. You really only have to worry about negative answers if you're talking about within the xy axis. And for our last problem in this video and in this section, we're going to use the figures to find the exact value of each of the trigonometric functions. This time, our function that we're dealing with is only in terms of theta. Okay, so we don't need the alpha picture, we just need the theta picture, and we don't have a drawing for theta over 2, we just have a drawing for theta. So the thing is, I'm going to have to convert sine of theta over 2 to an equivalent expression with just theta, and cosine of theta over 2 to an equivalent expression with just theta. So that's going to give me 2 times, and then sine of theta over 2, if you have to go back and look, the formula is right here. It's plus or minus the square root of 1 minus the cosine of alpha over 2, and then cosine is plus or minus the square root of 1 plus cosine of alpha over 2. So one's minus and one's plus. So we've got, again, plus or minus the square root of 1 minus the cosine of our alpha is theta over 2. Remember, this is multiplication, times plus or minus the square root of 1 plus the cosine of theta over 2. Okay. Now we're talking about triangles again, not within the XY axis. We're talking about ratios of lengths of sides of triangles. Therefore, the negative actually doesn't make any sense in this case. We're only talking about positive lengths, so that's gone and that's gone. And when we talk about multiplication, it's all positive numbers. Okay, so now let's actually do the substitution. So we have 2 times the square root of 1 minus, now cosine of theta, looking at my theta picture, that's adjacent over hypotenuse, so 4/5 over 2, whereas the second square root is 1 plus the cosine of 4/5, because it's still cosine of theta, over 2. I multiply these together, that's going to give me 2 times the square root of, okay, so that's going to be, because they're both under square root, I can just simply multiply them together. 1 minus 4/5 times 1 plus 4/5, and that's all over 4. Okay, now 1 minus 4/5, if you need to, find your common denominator. So that's going to be 5/5 minus 4/5, and then 5/5 plus 4/5. So I have 2 square root of 1/5 times 9/5, all divided by 4. So that's 2 square root of 9/25 divided by 4. Need to put that over 1 so we can invert and multiply. That's 2 square root of 9/25 times 1/4. And that's 2 square root of 9/100. Look how nice that turned out. It's 2 times 3/10. The 2 and the 10 cancel to give me 3/5 as my final result. Okay, that's the end of this section. Hope that helps.